today we're going to start our unit on differential equations. And so in this first section, we're going to be looking at what a differential equation is. We're going to be looking at creating slope fields and a couple of other things. So we're going to start today by just kind of thinking about what a differential equation represents and how we can find both general solutions and particular solutions to a differential equation. So a differential equation in x and y is going to be an equation that involves x's, y's, and derivatives of y. And it could be the first derivative or the sixth derivative or whatever. So both of these are examples of differential equations. And this is different from a regular equation. They're differential equations because not only do they contain x and y, but they contain derivatives. Here's one right here that has a dy dx, which is the same as the derivative of y with respect to x. Okay, so any function y equals f of x would be considered a solution to that differential equation if that equation is satisfied with y and its derivatives are replaced by f of x and its derivatives. So an example, we could show by taking derivatives and using some substitution that y equals e to the negative 2x is a solution of the differential equation y prime plus 2y equals 0. And again, let's kind of think about how we would know that. We can test to see, is it a solution or is it not? I know what y is, but I also need to know what y prime is. So using our derivative rules, y prime in this case would be negative 2 e to the negative 2x, using the chain rule there. So when we plug in, we're going to plug that in for y prime. So negative 2 e to the negative 2x plus 2 times the original y, which was this equation. So e to the negative 2x. And we want to decide, does that equal 0? And well, you can see here we're going to get negative 2 e to the 2x plus positive 2 e to the negative 2x, which does in fact equal 0. So we can verify that y equals e to the negative 2x is a solution to that differential equation. If it had come out to be not equal, then we would say, no, it is not a solution to that differential equation. So that's the way that you can kind of check, okay? Now, one of the things that we're going to be able to see is that we can find the general equation, the general form of the solution where we have some constant c. Now, everything that we've looked at when we've done integration and antiderivatives, you get that plus c. What we're going to see now working with differential equations is it may not always come out to be plus c. C might come in all sorts of different ways. So for example, the general solution to the one that we were just looking at is actually y equals c times e to the negative 2x, where c is any real number constant, okay? Anything that contains that constant c is called a general solution. So just the last bit of vocabulary here. The order of a differential equation is determined by the highest order derivative in the equation. So for example, y prime equals 4y is a first order differential equation because the first derivative is as high as it goes. S double prime of t equals negative 32 would be a second order because the second derivative is the highest that it goes. Okay, so again, using the same process as I sort of showed you above, we can decide whether or not a function is a solution to a differential equation. So the equation that we want to look at here is y double prime minus y equals 0. So for all of these examples, A, B, and C, we know what y is, but we need to figure out what y double prime is to be able to substitute for that as well. So if we look at example A, y prime is going to be equal to cosine of x, and y double prime is going to be equal to negative sine of x. Okay, so that means now we want to plug in the value of y, and we want to plug in the value of y prime to see if our equation is true. So y double prime minus y equals 0 is what we are hoping to show. Well, y double prime is negative sine of x minus y, which is the sine of x, and that equals negative 2 sine x, which is not 0. So the answer to this one would be no. It is not a solution to that differential equation. Okay? Take a moment to try example B and C. Go ahead and put your video on pause and try that on your own if you would like. Hopefully you got yes for both of these. So when you work through successive derivatives on B, you end up that y and y prime are exactly the same. So when we subtract, we get 0. On part C, remember that this capital letter C represents some constant. So that's just a constant multiplier. It's just going to work its way down through the problem. And so you end up getting yes for both of those. Okay? Now, geometrically, when we find the general solution, which includes the C, just like when we did antiderivatives, what you're finding is an entire family of solutions, because C can be any real number, so it can change what function it is that we're looking at. So, for example, and we're not going to focus so much on solving these in a lot of difficulty and for a couple sections still, but if I give you the differential equation x y prime plus y equals 0, you can show that y equals c over x is a solution to that differential equation. This graph over here to the right shows you all sorts of different ways that could work. For example, if c was equal to 1, then this black curve and this black curve represent that graph. That's the graph of y equals 1 over x. If c was equal to -1, that's going to reflect it, and we get this curve that's highlighted here. You could use c equals 50, c equals -2/3. It can be anything, and that's going to affect the graph. But do notice that they all make the same type of graph. It's just different transformations. So if we are given an initial condition, then we can determine the particular solution that goes with that initial condition. And so that's what we're going to look at here is just a couple examples of, well, just one example of that for today. Okay, so example 2 says for the differential equation xy prime minus 3y equals 0, first verify that y equals cx to the third is a solution. Then find the particular solution determined by the initial condition y equals 2 when x equals -3. So the first thing that we need to do is find the first derivative of y so that we can plug it into our equation. Y equals 3cx squared would be your derivative. Again, remember, c is just a constant. So if it was 2, the derivative would be 6x squared. We just don't know what it is just yet. Okay, so now we want to go ahead and plug in y prime and y to verify that when we subtract the way that it's defined, that we do get 0. So let's take a peek at that. So we've got it all subbed in. Now when we multiply, x times 3cx squared does give us 3cx cubed, and 3 times cx squared gives us minus 3cx cubed. So that does in fact equal 0, which means we have verified that that is in fact a solution. We end up with a true statement. Okay, now in order to solve for c, we want to be able to plug the value for x and y into that general solution. So again, we're starting with a general solution of y equals cx to the third. But we know that what we want to find here is we want to know when y